Sentinelle et Guindesat que le Sénégal a lancé. Et à propos de Guindesat, vous avez dit que c'est un mini-satellite. J'aimerais savoir qu'est-ce qu'un mini-satellite, quelles sont ses limites. C'est défini, bon, c'est en fonction de la zone de couverture ou bien pourquoi vous avez parlé plutôt des mini-satellites.
Oui.
Et j'aimerais aussi savoir quel est l'intérêt pour un État d'avoir son propre satellite. Est-ce que les données que les autres États, tels que les États-Unis et l'Europe, ont déjà mis à disposition ne suffisent pas?
Oui.
Merci.
Très bien, c'est une très bonne question, merci. La première, déjà sur le terme de... Donc, c'est pas mini-satellite, mais nano-satellite. Donc, ce qu'on appelle un nanosatellite, donc c'est un satellite miniature, donc qui va déjà être moins volumineux qu'un satellite classique d'observation de la Terre, et également donc moins volumineux. Donc, qui dit moins volumineux dit également qui pèse moins. Voilà. Donc, on va pouvoir l'envoyer plus facilement, donc à moindre coût. Ça coûte moins cher également à développer. Voilà, mais par contre, au niveau de la durée de mission, on va avoir peut-être une durée, voilà, qui est un peu plus inférieure à un satellite voilà, normal, quoi. Et sur la deuxième question de quel est l'intérêt d'avoir son propre satellite, donc Landsat et Sentinelle sont des programmes mondiaux reconnus, accessibles publiquement, mais si demain, voilà, un État ou un autre décide de privatiser ces données, donc qu'est-ce que les États qui n'ont pas accès à la donnée spatiale, qui n'ont pas accès à leur propre satellite, qu'est-ce qu'ils font? Donc, voilà. Si ces États-là décident de privatiser, de les rendre commerciaux, voilà, qu'est-ce qui se passe? Donc, c'est d'abord une question de souveraineté. Voilà. Et je pense que les nanosatellites, donc, ça coûte déjà moins cher à fabriquer qu'un satellite normal. Et donc, pour avoir cette souveraineté-là, donc, il est intéressant pour un État donc, de disposer de son propre nanosatellite d'observation de la Terre. Et en complément, donc, on a Landsat dans la Sentinelle, mais si par exemple demain le Togo se dote de son propre nanosatellite, donc ça va être une donnée en complément donc de Landsat et Sentinelle. Peut-être Landsat va acquérir une image le lundi, le Sentinelle va acquérir une image le mardi, et le nanosatellite togolais l'acquérira mercredi. Donc ça fait plus de couverture, donc je dirais. Voilà.
Merci. Nous avons une question en ligne maintenant. C'est celle de savoir quelles sont les techniques de pré-traitement des données de télédétection qui améliorent les performances des modèles d'apprentissage profond.
Question plus technique, intéressante. Non, un modèle d'apprentissage profond dans le deep learning en soi, il ne requiert pas énormément de pré-processing. Donc, à titre personnel, il m'est arrivé de faire des expériences donc sans et avec l'utilisation d'indices spectraux, donc, comme le NDVI que je vous ai présenté, et d'obtenir tout à fait les mêmes performances. Donc, un réseau d'apprentissage profond est capable d'extraire, comme le disait le docteur Apeke, donc d'extraire des représentations, des features caractéristiques pour le problème qu'il va solutionner. Et il ne requiert donc pas donc c'est toutes ces étapes de pré-traitement ainsi de suite qu'on peut avoir avec des modèles classiques de machine learning. Par contre, ce qui est important quand même en pré-processing, donc c'est de bien nettoyer ces données. Donc, si vous envoyez des données qui sont bruitées à votre modèle, donc normal, vous obtiendrez des résultats qui ne sont pas cohérents. Donc, quand je dis filtrer, nettoyer, donc c'est par exemple, on a des acquisitions qui sont nuageuses. Donc, vous faites apprendre à votre modèle des acquisitions qui contiennent des nuages qui ne sont pas masqués, par exemple. Donc voilà, votre modèle va vous donner des résultats incohérents. Donc, faire par exemple du pré-processing dans ce sens-là, donc ça s'avère quelque chose d'utile et d'indispensable, je dirais.
Merci beaucoup. Pour le moment, plus de questions en ligne, mais on a une petite dernière question dans la salle. Et voilà, vous avez le micro sur cette table. Allez-y.
Merci. Merci beaucoup pour votre présentation.
Allez, s'il vous plaît.
Merci beaucoup pour la présentation. Donc, dans cette présentation, vous avez parlé d'occupation des sols et vous avez utilisé Landsat, il me semble. D'après vous, dans l'état de l'art actuel, avec les technologies actuelles, qu'est-ce qu'on peut reconnaître au sol actuellement par apprentissage renforcé? Jusqu'où on peut aller? Là, on parle d'occupation.
S'il vous plaît.
Actuellement, avec les technologies actuelles, à part l'occupation des sols, jusqu'à quel niveau de détail on peut aller en reconnaissance d'images à partir du satellite?
Ah, ok. Bon.
C'est une grande question.
Ouais, très bien. Merci pour la question. Donc, ça va dépendre, pour aller directement à la réponse, ça va dépendre donc, de la donnée en entrée. Donc, si on a du Sentinelle ou bien du Landsat, donc Sentinelle c'est 10 mètres maximum, Landsat c'est 30 mètres, donc on ne pourra pas détecter quelque chose donc, qui est plus fin que 10 mètres ou bien 30 mètres. Donc, par contre, dans les applications militaires, donc, ils ont des données donc, qui sont privées, privatisées, où ils peuvent aller jusqu'au centimètre. Donc, il y a Pléiade Néo de Airbus à Toulouse en France qui vend des données commerciales à 15 cm. Et ça fait des données super précises, donc également pour des applications militaires. En application civile, on n'a pas vraiment accès à ces données-là. Et pour des applications type occupation du sol, donc, allez, on peut avoir jusqu'à... Il y a Spots qui a jusqu'à 1,5 mètres, et il y a PlanetScope qui a jusqu'à 3 mètres. Voilà.
Super, merci. Ok, on a une question. Est-ce qu'il y a d'autres questions dans la salle? Comme ça, je prends déjà toutes les mains. Une, deux. Est-ce qu'il y en a encore? Ok, donc on va prendre ces deux questions et passer à la suite. Non, d'abord le monsieur sur la première table et ensuite la deuxième table. Merci.
Alors, merci pour votre présentation. Pour obtenir les classes d'occupation, vous avez utilisé la classification non supervisée. Donc, j'aimerais savoir pourquoi avoir opté pour la classification non supervisée au lieu d'utiliser une méthode de classification supervisée. Merci.
Ok, je rectifie. C'est pas une approche non supervisée. Quand on dit adaptation de domaine non supervisé, plutôt, c'est ça? Ok. Quand on dit adaptation de domaine non supervisé, c'est qu'on a des labels dans le domaine. Donc, domaine, là, en particulier, c'est les années où on a de la vérité de terrain. Et on essaie d'aller prédire dans une année où on n'a pas de vérité de terrain. Donc, c'est là le non supervisé un peu. Donc, et ça vient, concrètement, ça se traduit par le fait donc avec cette hypothèse-là où on peut avoir des cultures qui sont les mêmes, ou des parcelles qui ne font pas de rotation culturelle entre 2 années. Donc, on peut avoir donc, ces pixels qui ont le même label entre les 2 années. Et donc, dans une année A, où on a la vérité de terrain, on a un profil qu'on connaît. Et dans l'année 2, où on n'a pas de vérité de terrain, donc on va justement avec cette hypothèse-là aller voir quel est ce profil-là. Et donc, à partir de ce profil, on génère donc, des labels, des pseudo-labels. Donc, à partir de cette hypothèse, et donc on essaie de récupérer un peu donc, les pixels qui sont similaires dans l'année où on n'a pas de vérité de terrain. Donc c'est un peu ça.
Merci. Donc la dernière question dans la salle maintenant.
Merci.
Est-ce que vous pouvez lever la main pour que je vois?
Moi?
Ah, pardon, ok.
Oui, c'est moi. Et Monsieur Freitas, informaticien. Bon, je reviens sur la souveraineté nationale. Et je suis souvent surpris, malgré l'évolution technologique, les données satellitaires, qu'aujourd'hui les gens se donnent du plaisir à lancer des drones à gauche, à droite. Est-ce qu'il ne serait pas intéressant pour un pays comme le Togo, en face des défis climatiques, des défis liés à l'agriculture, et pour terminer, le défi de nos populations dans le Nord, qu'on puisse nous-mêmes avoir ce nano-satellite-là. Est-ce qu'il n'est pas vraiment temps? Parce que ce qui m'étonne dans ce pays, on a des capacités, on a des compétences, des experts, des talents variés, mais c'est comme tout ça là, ça ne sert pas à grand-chose. Je m'excuse de le dire ainsi. Et votre exposé me confirme encore dans cette vision que j'ai du Togo, qui est un pays vraiment qui peut aller très loin, plus loin que là où il est aujourd'hui. Donc personnellement, si cette possibilité, vous pouvez aider les gens, même le gouvernement, à aller dans ce sens-là. Je vous encourage. Merci.
Ok. Je pense que c'est plus un commentaire qu'une question. Donc, oui, je partage totalement votre avis que on pourrait faire plus en Afrique, en l'occurrence au Togo également, se doter de nos propres moyens d'observation de la Terre s'il le faut.
Ok, merci beaucoup pour ces réponses, ces questions. Et peut-être la dernière intervention, afin qu'on passe à la session suivante, ça sera donné au docteur Apeke, qui a un petit mot de 30 secondes.
Bien, merci docteur Bojo. Je profite toujours de l'occasion pour glisser quelques petits trucs par rapport à la question du doyen. Je me permets de l'appeler doyen. Aujourd'hui, encore une fois, il y a beaucoup de choses qui sont lancées. Normalement, demain, il devait y avoir une présentation, mais comme on a beaucoup fait sur les satellites, je vais juste faire ma présentation en 30 secondes en même temps. Pour le Togo, on a essayé, par exemple, d'utiliser ces technos pour prédire les zones successibles de déforestation, par exemple, à partir des images satellites, mais plutôt sur la seconde approche par du combe LSTM, pour pouvoir justement redimensionner. Ce qu'il n'avait pas dit, les satellites sont souvent les channels, c'est plus long. Il y en a 13, par exemple, si je ne me trompe pas, hein, sur les images satellites, alors que les images habituelles, les channels, c'est 3. Et donc, il y a eu beaucoup d'autres techniques pour justement redimensionner déjà et d'essayer de prédire les zones successives de déforestation. On a fait la même chose pour les zones successives d'inondation. Donc, c'est pour vous dire que on essaie, le chemin, il est long, mais on va essayer aussi d'apporter des solutions aux Togolais grâce à l'outil IA. Merci.
Merci beaucoup. Nous allons raccompagner le docteur sous vos ovations, s'il vous plaît. Alors, ça, c'était la session du docteur Jean-Eudes Bodjan, qui, depuis 2021, travaille un peu sur certains sujets de recherche, notamment l'amélioration des systèmes de suivi des cultures à l'aide de la télédétection. Comme vous l'avez suivi, nous avons pu comprendre comment, avec l'apprentissage profond, on peut arriver à améliorer la précision de la classification des sols à partir des images satellitaires de qualité variable avec des données limitées. À présent, nous allons passer à un deuxième atelier qui va être aussi un peu technique avec un expert qui est parmi nous ici. Et pour pouvoir annoncer cet atelier, d'abord, je vais encore préciser quelques dispositions. Vous avez les casques de traduction sur les tables pour pouvoir suivre en français parce que ça va se dérouler en anglais pour les gens dans la salle. Pour ceux qui sont en ligne, vous avez le bouton en forme de globe où vous pouvez trouver la chaîne française et la chaîne anglaise selon la langue dans laquelle vous êtes plus à l'aise pour pouvoir suivre cet atelier. Il sera un peu plus technique et donc nous vous invitons à suivre très attentivement. Il faut mentionner que pour cet atelier qui va suivre tout à l'heure, c'est en partenariat ou dans le cadre de la collaboration du gouvernement togolais avec l'université de Berkeley. Et donc, c'est l'université avec laquelle le Data Lab du ministère de l'économie du numérique et de la transformation digitale sera co-créé. Et donc, c'était pour ce Data Lab, justement, qu'il y a eu des recrutements récemment qui ont été effectués à travers le challenge réalisé avec Zindi sur la prédiction de la fibre optique. Donc ça, c'est un rappel important à rappeler. Et maintenant, je vais inviter, avant de l'introduire, je vais inviter notre expert qui va venir tout à l'heure. Il est un data scientist et il a travaillé plusieurs années sur des projets divers reliés à l'imagerie satellitaire plus le machine learning. Donc, il s'agit du docteur Colin Molitor, que je vous prie d'ovationner pour l'introduire ici sur scène.
Hello, everyone. My name is Colin Molitor, and today I will be talking about how we can combine satellite imagery with machine learning to address global challenges. So before we get started, I did want to mention that all of my materials today will be in English, so I do apologize for that. There's going to be 3 components to this that could be challenged by the Wi-Fi availability, but the first part is a lecture. I'm then going to go through a demonstration of Mosaic's technology, and ideally we will do a hands-on session at the end where we can have everyone work together in groups to solve sample problems that I've put together. There will be a short survey at the end of this slideshow. I'm hoping everyone can fill it out if they want to participate, so that we can kind of make groups based on their technical skills. We're looking for people that are familiar with Python to help people who maybe have never used it before. And that will be done through Google Collaboratory. And then I wanted to give some time at the very end for each group to present their results and what they learned from the hands-on session. This will be kind of a long workshop. There will be some technical language. Feel free to interrupt me if something does not translate well into French. And I could always try to re-explain something in different language. So, just to refocus a bit, we're going to be talking about how to combine satellite imagery and machine learning, as we just heard from the previous presentation. This one will be a little bit different, but similar methodology. So the first thing we need to understand when we look at this field is that there are large data gaps. And here we can see the average interval between economic surveys going back to 1993. And you can see that much of the world lacks crucial data on economic development. And you can see, especially in Africa, there are very few surveys, or they happen very far apart. Similarly, with agricultural censuses, there's often very long periods between agricultural surveys, which really limits our understanding of crop production across the world. You can see many parts of Africa, especially in Central Africa, simply have never done agricultural censuses before. About 25% of countries have gone more than 15 years since their last agricultural census. And this is very important because as future climate changes, we might expect yields to go down. And so we really need to understand the current state of agriculture. We also have kind of sparse data when it comes to population density and population characteristics, with about 6% of countries have gone more than 15 years since their last population census. In the natural world, you can see that much of these gray grid cells in this map represent areas where we just don't have any digitally available data on species distribution. And where we do have data, it tends to be in the US, Europe, and Australia. And pretty much all of South America, Africa, and Asia has very limited data, which really limits our ability to understand the world's biodiversity. And these data gaps exist because traditional data collection is very expensive. For example, one demographic and health survey in one country for a single year can cost as much as $2 million US. In America, these numbers grow even larger, with the American Community Survey costing more than $200 million every single year. Similarly, agricultural censuses can be very expensive to implement. And this means that data gaps are largest where our social and environmental challenges are most pressing. And we need to understand how we can fill in all of these data gaps so that we can better understand what the future is going to look like and how we can meet sustainable development goals. So one potential solution is satellite imagery, and currently there are over 700 Earth observation satellites in orbit, collecting more than 100 terabytes of data per day. This satellite imagery could be used for all sorts of problems, including measuring irrigation or crop yields, as we just saw from our previous presentation, or urbanization and economic growth, or the extent of flooding or other natural disasters. Now, satellite technology has continued to improve throughout the years. We can see some publicly available satellites on the top row here, from Aqua Modus to Landsat or Sentinel constellations, as well as publicly available data sets on the bottom row. And you can see that these satellites, especially the PlanetScope, are much smaller, they're much lighter, they're easier to launch into space, and they also collect higher resolution imagery. So here we can see an area where the Modus sensor, you are not able to resolve very many details, and as you go across, we start to improve our resolution. And when it comes to the commercially available satellites, that grows massively. There's also varying degrees of temporal resolution. So that's how often does a satellite revisit a place on Earth. And some of these satellites revisit very often, or they're in a constellation of satellites that allows them to image the Earth one or sometimes even twice a day. But all of this data presents a massive challenge because this data, and especially the higher resolution imagery, has very large file sizes. You need big servers, you need all sorts of technology to even process this imagery. And we need to understand how we can go from imagery to solving problems. And so the question then becomes, how do we transform unstructured, pixel-level data into structured and useful information? The modern answer to this question tends to be deep learning, which is a type of machine learning with artificial neural networks. In this example image, we can see that we have an input image of a car. It goes through some fancy mathematical operations, and at the end of the day, you're able to make a classification of what is inside of that image. This sort of technology has been used in the past to measure forest cover. Here we can see global forest cover, as well as where we're gaining forest and where we're losing forest. It's also been used to make measurements of wealth, and it tends to be much higher resolution than other types of data that is currently available. We've also been able to use this to measure things like surface water and other natural phenomena. But each one of these measurements is a major research enterprise, usually combining large teams of people. It costs a lot of money. You need specialties in computer science, in satellite imagery, in statistics, and all of these different things, which makes it very expensive and very hard to conduct this type of research. But we do know that many people would like to combine satellite imagery with machine learning to solve their own problem in their own specific settings. But the limited access to data or compute power or expertise prevents most researchers and decision makers from using satellite imagery and machine learning to solve their problems. And these barriers imply that most remote sensing is conducted in developed countries, usually at large universities that are well funded. So we're developing a system that makes satellite imagery and machine learning easy, and cheap, while still maintaining performance competitive with other leading models. And because it's cheaper and faster, we're also able to do more modeling to characterize our uncertainty and measure the sensitivity of our performance. And we call this system Mosaics, which stands for multitask observation using satellite imagery and kitchen sinks. And this process starts off with a set of geolocated images, which then go through a one-time unsupervised computation where it's kind of a black box. The imagery goes in, and we get out of that a data frame that we can use. And in this matrix here, we have every row represents an image, so like a physical location on Earth, and every column will represent some feature of that imagery at that location. Now, this massively compresses the size of the data from the satellite imagery, so it's much smaller data files and much easier to work with. We can then pass those data files off to user number 1, who is interested in forest cover. And the important part here is that they already have certain information on forest cover at specific locations. So they can take their forest cover data, join it to our satellite features, and solve a linear regression. They can recover those coefficients from the regression model and then make linear predictions for all of the areas from which we've computed features. So at the end of this, you get the same number of estimates as you put into the model of forest cover, even if you don't have labels for all of these locations. And the advantage of the system is that we can also have a second user who comes in and wants those satellite features, and they join it to their data on population density. They do the same process, build a similar model, and make the similar predictions on population cover. Both of these users never have to touch satellite imagery. They don't have to go through the hassle of processing or computing these complex features, which is really nice. So this whole system can be compared to traditional convolutional neural network models, which learn domain-specific features. So deep learning methods customize to a single metric, for example, poverty. But each image contains information about potentially hundreds of outcomes. On this plot, we can see a gradient of population density on the y-axis. Oops. Oh no. And on the x-axis, a gradient of forest cover. So we should be able to extract information from this imagery that allows us to learn about both of these outcomes. And the solution is to generalize instead of customize. So Mosaics accomplishes this by computing a single mathematical summary of that satellite imagery that anyone can use without any modification to then accurately predict many different ground conditions. So I want to step back to what's that inside of this black box and how does this process actually work. So we start off with a sample set of imagery, and we draw weights for our model from the imagery itself. And these are drawn completely at random, and we use those as the weights in a neural network model where we're able to summarize the information from each image that represents one of those little patches. And each little patch summary ends up becoming a scalar vector, scalar value in our feature vector. So what this means is that we can take an example image, we can draw a sample patch from that image, In this case, we are drawing a patch from the forest canopy. So we can see that this patch is very green. In the second patch, we're drawing it from this road network. So the patch tends to be very gray. Now, once we've done the convolution and summarization, that patch becomes a single value. And in our third patch, we have drawn it from our water, so that is a very blue patch. Now, each one of these becomes, like I said, a value in this vector that represents the image, and it represents the location. So if we have a second image, we can start to see that the bottom image has less green, more gray, and no blue, which is why these values are different for each image. And then you could have labels for forest cover, and you're able to build a model where you're able to model forest cover as a function of those satellite features. User number 2 can have information on road networks, such as road length. Or user 3 could have information about water. And finally, with population. And I want to pause at population because with the imagery and the resolution that we have, we're not able to measure people directly. So instead, we're measuring other things within the image. In this case, more roads could be indicative of more people, or more buildings, or something along those lines. So for the rest of this talk, I want to go over how this system works across different tasks, followed by how we can scale up mosaics to unlock the global satellite imagery's full potential, as well as a couple of use cases of this technology, how we're working to increase accessibility, and then the limitations of this process. So first up is the performance of mosaics across different tasks. So we start off with the United States because there's a lot of available data, and so it's an excellent place to test these methods. So we use imagery from Planet Labs. It's about 4.7 meter resolution, so it's pretty high resolution. We then compute 4,000 random features of that imagery. We can then join those features to our ground labels. On the left of this plot, you can see our labels for forest cover. We can make our regression using the satellite features to produce predictions that you can see look very similar to the labels. And finally, we're able to measure this performance on the right-hand side of this plot by plotting the observational values against the predictions from the model. And we can see that this model is able to explain about 91% of the variation in our forest cover labels using our satellite features. This process is very simple, and you can see it can be done in just a few lines of Python code. In domain number 2, we are going to look at population density. And you can see our performance is not quite as high as the forest cover. And this is important to know that we're not, like I said, we're not measuring people directly. So instead, we're looking at how many buildings, how many roads, and all these sorts of things. So it's more of a proxy. But despite that, we're still able to get pretty promising performance and pretty good results out of these models. Here we're looking at elevation. You can see that one of the things with mosaics is that we're looking from a constant perspective from the satellite down at the Earth. And so it's harder to resolve elevation versus other outcomes because it might look very similar. And despite this, we're still able to explain about 70% of the variation in elevation with our satellite features. In this example, we are measuring nighttime luminosity with daytime satellite imagery. So this is another outcome that is measured by proxy, but we get much better performance than we do with population density. And this is because it's pretty easy to see that a building or a street might be lit up at night. Here we're looking at the average house price across the United States. And now we start to see the performance decline substantially. And this is because average housing price has many more factors that influence it besides what it looks like from space. So here we're looking at total road length, which is very similar in performance. And one of the problems with this whole process is that it relies heavily on the labels. And in the United States, while there is excellent data for many different outcomes, this is one where the data can be lacking because private roads are usually not recorded in many states. So while there might be a road physically there, it might not be in the data that we're using. So it's very important that the results of these models are very dependent on the data that you have of your ground conditions. And in our final outcome, we're looking at income per household. And this outcome has many of the same problems as average housing prices. And it's just a very difficult thing to measure from space. Despite this, we're still able to explain a pretty substantial amount of the variation in those labels. Now, taken all together, the important thing to remember is that all of these outcomes were measured with a single encoding of satellite imagery. So they all share the same features. So now I want to talk about how competitive is this method with more traditional convolutional neural networks. So here we're looking at the R-squared values from the plots we were just seeing, now as a bar plot on the y-axis, and each outcome is on the x-axis. We can compare this against a pre-trained convolutional neural network, and you can see that our performance greatly is much higher than in this method. So then we could look at a more sophisticated model, in this case a ResNet 18, and we see that this now does better than Mosaic's, although the performance is very comparable. And so then you would have to ask yourself, why not use the more complex model, which clearly does slightly better? And the answer is because Mosaic's is so much faster, anywhere from 250 to 10,000 times faster to train than a convolutional neural network. We see that the CNNs for both of these take somewhere around 8 hours per task versus Mosaic's, which can take as little as 3 seconds when using a graphical processing unit, or as many as 2 minutes if just a simple laptop. I'll go over some examples later for the demonstration where you can see just how fast it is. And this is very important because consequential decisions are increasingly dependent on satellite imagery and machine learning output, such as which family should receive financial assistance. In this example, it's the Novici, where they're delivering financial assistance to people in Togo, where they're able to use high-resolution imagery to map poverty rates across Togo and deliver more targeted aid across the country. And this is very important that Mosaic's computational efficiency allows us to measure how uncertain we are, whereas retraining convolutional neural networks in the same way would be computationally prohibitive. So we're not able to get a similar sense of our uncertainty in the model estimates. So now I want to look at how this model performs when you train in one location and then test in a totally new location. So it's a form of spatial cross-validation. And you can see on the x-axis these grid cells across the US will vary in size. So they'll get larger the further out you go. And you can imagine splitting up your data, say you're training on those black grid cells, and then testing on the white grid cells. So we start off by showing the performance of forest cover with our spatially overlapping samples, where we don't do any sort of cross-validation on the spatial component. And then we start to vary the size of those grid cells, and you can see that we're able to maintain a strong signal even across very large spatial distances, although our uncertainty does grow larger. We can then compare that to a more basic spatial interpolation. And you can see that the performance massively declines, and the uncertainty grows much larger with this much simpler method. So we can repeat that for all of our different outcomes. And you see that Mosaic substantially outperforms spatial interpolation across all of our tasks, except for elevation and housing price. And for elevation, this makes sense because it is spatially confined to be continuous. So a simple interpolation, just connecting the dots, tends to actually work pretty well. So next I want to talk about how we can characterize our uncertainty, or measure our model sensitivity, sorry. And so we do this by varying the number of satellite features that go into our model, anywhere from maybe 100 up to about 8,000. And then we are also able to vary the sample size that we put into our model. And we see that a majority of our signal is recovered with using as little as 200 satellite features, or as few as 500 training points. Although as you go out along these, on the x-axis for both of these, the performance does improve. So now I want to talk about how we're able to scale up mosaics to unlock imagery's potential across the globe. And so we wanted to ask which variables can be effectively measured and what are the most compelling applications. So to do this, we start off with a set of satellite imagery across the full globe this time. Similarly, we will compute 4,000 random convolutional features for every location on Earth. We'll then go about collecting 120 different publicly available data sets in a variety of different structures and categories, anywhere from agricultural assets to agriculture like yield, things of that nature, as well as infrastructure, and many other socioeconomic outcomes. So here are the different categories, and here are the number of labels we have for each one. So we can start off by just looking at a few examples from this research. And we're going to start off with one of the better performing ones, maize yield. So we have labels from across the United States, Brazil, and Europe, as well as some areas of China and Asia. And you can see that we recover a very strong signal in our maize yield from these satellite features. Next, we're going to look at road length. And this time, instead of just the US, where we have really high quality data, we're looking at the rest of the world. And so now the data is even more, more challenging to work with. But despite this, you can see that we're still able to recover a very strong signal in road length. Here we're measuring the International Wealth Index, which is similar to the process that was used for the Novici project in Togo. And this does very well. We're also able to use, We're also able to use it with demographic and health surveys to look at things like malaria in children from age 6 to 59 months. And you can see that the signal is not quite as strong. And during my demonstration, I will show you an example of why this is challenging. So keep that in mind for later. Here we're going to look back at the US again, where we have data on petroleum pipelines. And this is an example where the process completely falls apart. And this is because pipelines in our data are generally not visible. Most of them are buried underground. So of course we're not able to see them from satellite imagery, therefore not able to recover a signal in our models. So here are all 120 plus tasks across all of our different categories. You can see that this is kind of a lot of information. It's really hard to take in. So instead, we can group just the performance values into a box plot for each of our categories. And you can start to look at the variation both within tasks and categories and across categories. So on our first plot, we can see the difference between buildings, which does very well, with our pipelines, which basically doesn't work at all. And then you can see that the category, depending on what category you're in, your performance starts to increase as you go out towards the end of the x-axis. And what we find is that human and natural systems do not systematically differ. And that means that a tree in Asia can look very similar to a tree in Africa or South America or anywhere else on Earth, as well as a building can look very similar in all of these locations. So next, I want to talk about how you can use mosaics to increase the spatial resolution of traditional data collection systems. We will be looking at the Human Development Index provided by the UN, which measures how long and healthy your life is, as well as how much knowledge you've acquired, and your standard of living. And this has been used in policy and in research to assess many different human development outcomes. The problem with this data is that it comes in very large spatial blocks, which means that it's harder to get at the local scale to do more targeted interventions and provide aid. So in this map, you can see that this data is at the first subnational level, so states or provinces. And you can see the larger picture of the globe and where different areas fall into this index. But what you can't get at is what is the development level of a village or a town. So what we do, because we have our labels that are these very large polygons, we can summarize our satellite features to those same polygons and build a model, but then apply it to the satellite features which are at a much higher resolution. So you can start to increase the resolution maybe 2 times or 4 times. A little bit of a delay here. Getting all the way back down to the image level. And so this is really important because this really allows us to get a much better picture of what the Human Development Index looks like at these much smaller spatial scales. So here again is our map we were just looking at with the big spatial blocks. We are then able to go to the second subnational level. So it could be districts or counties or that sort of level. And so you can start to see that there's more complex spatial relationships with this development index. And then finally, we're able to make predictions at the image level. And in this case, we are masking out the population. So if there's no population that lives there, there's no reason to measure the development in that area. But now you get a much finer picture of what human development looks like across the globe. Now in our use case number 2, we're going to use mosaics to fill in spatial and temporal data gaps in traditional survey-based data. In example number 1, we're going to look at agricultural surveys in Zambia, which were halted during the COVID-19 pandemic, which delayed critical information on crop yields and limited our ability to understand food security indicators. So we used mosaics along with, so we used historic crop yield data from Zambia, as well as publicly available Landsat and Sentinel imagery to build a model and then start to get a sense of how these yields did in these years where they were not able to collect data. In example number 2, we have suspected mining locations of small and artisanal scale mining. And you can see that the labels are very sparse. So it's just these little points on this map. But we're interested in knowing what is the footprint of small scale mining across the full continent. So we use this label data to build our model. And then we can apply mosaics across the continent to both fill in spatial gaps within a country and to move on to new countries where we didn't actually have data that put into the model. Again, we're masking out areas where we have very low confidence. And these are just estimates. So each pixel might not actually represent a mine, but you can start to get a sense of where the hotspots of mining actually are occurring. So next I want to talk about the work we're doing to increase the accessibility of mosaics with a public API as well as training resources. So currently we have api.mosaics.org. It's still in development, so it's like kind of in the beta version. But even now you have access to global pre-featurized imagery, as well as video demonstrations and replication code, tutorials, and examples. And soon, once we publish the predictions that we've been making in these other research endeavors, all of these will also be available. So you won't even have to go in and make the model for human development yourself. You'd simply be able to download our high-resolution predictions. Let's see, just zoomed in more. So these will be available. There's going to be about 115 maps that we plan on publishing. Yeah, 115 maps, and there's no real point to publishing things like petroleum pipelines because it just doesn't work. But all of this is available, or is and will be available, as well as different replication code and features. And in the demonstration and hands-on session, I will also be sharing example code that you guys can all have access to. So we've seen that this can be very powerful, but we need to know what are the limitations. And the largest limitation of this methodology is that, and this is true for all machine learning, and it's the predictions that come out of a model are only as good as the ground data that we are training on, which means that conventional data collection efforts remain absolutely essential. We cannot do this research without more data from on the ground. And we also know that machine learning tends to have algorithmic bias. And this is insufficiently studied in the realm of satellite imagery and machine learning. We're working to correct that and try to understand which populations are we misrepresenting and what effect does systematic errors have on policy decisions, because this, at the end of the day, can affect real people. There's also some ethical concerns. And this tends to increase as the precision of this technology improves. For example, with the mining, where we're trying to map mining across the continent, you know, some of these mines are in conflict-ridden areas, and they're people. They're just trying to make a living. So you don't necessarily want to publish high-resolution predictions of where this is happening. But if you're trying to make policy on how to support these people, then it's really important to know where that's happening. So in conclusion, we can see that this technology holds substantial promise for filling in critical data gaps and supporting global sustainable development. But this potential has been, up till now, limited by the cost of modern deep learning approaches. And mosaics can make this technology accessible while also unlocking more information from each image. And you can see that from the 120 different maps that we've produced with a single image featurization at a low computational cost. And our API will allow you to generate your own imagery-based predictions without ever having to touch satellite imagery itself. And again, all of this code, input data, and output data are publicly hosted or soon to be publicly hosted. So then the question becomes, what can satellite imagery and machine learning help you solve? So I'd like to end here with some acknowledgements. This has been a huge research effort, just like all of the other convolutional neural networks. They take a big team. Mosaics, to develop this technology, has also taken a big team, which I am just a small part of. These slides will be available to you all, so there's the link as well as a QR code to access the API. And I'd also like to thank some of our partners in funding for making this work possible. And I want to leave this slide up for a few moments. There's going to be an interactive session after I finish with the demonstration. So if you could all just try to fill out this survey, it'll give me a sense of your technical skills and help me make groups. I will admit I was not aware that there'd be so many people in attendance. So, but hopefully we can all get people to use mosaics if possible. This will be done on Google Collaboratory, so Wi-Fi access has been extremely limited, and this might not work quite as well as I was hoping. But if you have a moment, please fill out the survey. It'll really help us pair everyone up, because I realize not everyone has experience with Python or machine learning, but I still want everyone to be able to participate if possible. So I'm going to pause for a moment. I'm going to get my laptop, and then I'll go on to a demonstration.
Merci à Colin. Encore une fois, juste pour rappel, le code QR était projeté pour permettre aux participants de pouvoir le remplir. Si on peut garder le code QR, s'il vous plaît, à l'écran. Comme ça, tout le monde essaie de scanner pour mettre un peu les compétences que vous avez. Ça va permettre de faciliter la constitution des groupes de travail qui aura lieu tout à l'heure. Donc, tout à l'heure, il y aura un groupe de travail, mais vous remplissez ce formulaire pour qu'on puisse savoir un peu comment on met un peu les gens en groupe. Donc, vous aurez besoin du Wi-Fi pour travailler tout à l'heure avec Google Collab. Et donc, ok, donc voilà, assurez-vous d'avoir répondu aux questions sur ce formulaire pour tout à l'heure. Donc, Colin va prendre son ordinateur et donc il va passer à la session de pratique interactive où il y aura des travaux de groupe. Donc, juste pour un petit rappel, Apprêtez-vous pour cela, assurez-vous au moins par table d'avoir un ordinateur connecté à Internet, si vous le pouvez. Après le formulaire, on pourra savoir un peu comment on organise les travaux de groupe.
So before we get started with the demonstration, is there any questions regarding the presentation? Yes.
Gonna use it at McGovern Foundation? Are some of the donors like UNDP and USAID and McGovern Foundation planning to use the work?
Yeah, so for example, with the McGovern Foundation, they are one of our partners in funding the work with the Togo Data Lab. One of the reasons we're here is to help get some new data scientists trained up in the use of this technology to allow more predictions, more different things to learn about Togo. There's some other funders that have went on to use mosaics, but not everyone. Some people just give us money and allow us to conduct research. Yeah. What's that? Yeah. We can take.
Alors, on va voir dans la salle s'il y a 2 ou 3 questions. Donc, je vais voir les mains d'abord. 1, 2, 3. Et on continue. Justin.
Okay, thank you very much for your presentation. I was just wondering if, in terms of tracking natural disaster in Africa, you have a lot of data set for that. And is it possible to have access to them at a friendly cost for organization in Africa?
Yes, thank you for the question. So one of the current limitations of the publicly available API data is that it is a single layer. So we don't have time series mosaics features on the API yet. We're hoping to increase the temporal resolution to get more features on there to make more immediate predictions available. Because that's one of the challenges with natural disaster is it doesn't necessarily matter what happened a year ago. You want to know what's happening right now. You can still use this technology. It just requires to go back to the imagery and to process like current satellite imagery. So with the Togo Data Lab that we're working with the ATD, I've computed a bunch of historic features, but we're still working on how to make that more relevant for like today. And it's a big challenge, but we're hoping to solve that soon.
Deuxième.
Okay. I noticed that before training the data and applying the ridge model, you always merge the data on location and longitude and latitude. So if I have to work with your model, do I have to always get the location data of what I want to use? Let's say for mining, I do have to collect the data location related before using the model?
Yes. So all of this does depend on your physical location and matching the features to the labels that you have. That doesn't mean that you can't then make predictions into new areas, but the geolocation is essential to the process. In certain tasks, like we saw with the Human Development Index, our areas that we're attaching features to are very large spatial blocks. So if you have a general idea of where the area is, you can summarize up to the confidence level. So a lot of survey data is randomly jittered to maybe 5 kilometers. So if you're not confident on where exactly something's happening, you can just increase your spatial scale until you're reasonably confident, and still, but it still does require a spatial joining of your ground labels to the satellite features.
Et la troisième question?
Merci pour votre présentation. Et dans le cadre de l'utilisation de Novici, par exemple, où on détermine quel foyer doit recevoir de l'aide financière, comment est-ce qu'on détermine le niveau de difficulté financière de tel ou tel foyer grâce à une carte? Les capacités financières ne se traduisent pas forcément via la manifestation matérielle. Donc, quel indicateur est utilisé pour cela?
Yeah, so I want to start out by saying I was not involved in that project at all, but what they did after using the satellite imagery to identify areas facing poverty challenges and identifying the cantons where they need to deliver aid, I believe they used call data records to target households. And I don't know exactly what that process looked like, other than there was other input data that was essential to making that aid targeted. And Sean can maybe speak more to that.
Hello. So the way it worked was the team first used satellite imagery to identify the lowest income or lowest wealth areas of Togo. And then within those areas, they looked at the call detail record data from the largest telecommunications company in Togo. I think it was Togocom. And the CDR data is basically, it's the metadata from people's mobile usage. So it's every time you recharge your phone with credits, every time you place a call, whether it's national or international, with location information. So each line in that database is a single time a single number does something on their phone. So they used a deep learning framework to extract useful features from that information to predict individual level wealth within the areas first identified through the satellite imagery.
Je vais juste préciser parce que ça concerne le ministère.
Oui, juste une petite information. Okay. Je vais inviter les participants de la table de à ma gauche de pouvoir prêter attention, s'il vous plaît. Ensuite, nous allons passer aux travaux de groupe où vous aurez plus de temps pour discuter en groupe. Merci.
Le ciblage qui s'est fait avec Novici s'est fait avec 2 modèles différents. Et on part de l'hypothèse que quand vous dites qu'on ne peut pas prédire le niveau de pauvreté avec le matériel, c'est comment dire, c'est vrai à demi-mot, si je peux dire ça, parce que c'est quand même un indicateur. Aujourd'hui, par exemple, le premier modèle qui a été utilisé pour déterminer les cantons les plus pauvres, ils ont utilisé par exemple l'image satellitaire de la carte de la nuit, on appelle ça, c'est le niveau d'éclairage. Ça permet déjà de savoir si vous êtes dans une zone qui n'est pas éclairée. Potentiellement, vous n'avez pas le même niveau économique que quelqu'un qui va se trouver par exemple dans une zone urbaine très éclairée. Le toit que vous avez par exemple de votre maison, si c'est de la tôle ou par exemple un toit à béton, c'est pas pareil. Donc avec ça, c'est des proxys. On ne dit pas que c'est précis à 100%, mais on arrive à approximer quand même le niveau de développement, par exemple, d'un canton, et on se dit que dans ce canton-là, à quelques exceptions près, il y a tel niveau de pauvreté. Ensuite, ils ont utilisé les données des opérateurs téléphoniques. Donc, vous avez un téléphone, la fréquence à laquelle vous êtes en train de recharger, comment dire, le crédit, en quelque sorte, est un indicateur, on va dire, de ce que vous avez dans la poche. Bon, maintenant, je tiens à préciser que ce sont des données anonymisées qui ont été utilisées, et donc dans le respect quand même d'un certain nombre de règles de protection de caractère. Souvenez-vous qu'on était en situation de crise et qu'il fallait trouver une solution. Voilà, merci.
All right, merci beaucoup au commandant. Une dernière question en ligne, on poursuit dans la salle. An online question. Je crois que ça fait 3 questions en une. Je vais rapidement lire ça et la réponse sera résumée. So, in the case of Togo, what are the factors of precision of the use of satellite imagery to predict the needs of the population? Are these data crossed with real financial data? In the context of our African countries, is it not proven that lightning or buildings are correlated with the financial health of the population? So what are the decision factors to be taken into account?
Okay, so the question is regarding African data on income or wealth? Or?
Yeah, financial data
okay.
In African context.
So we don't collect any of this data ourselves, so we're not doing the surveys. In the future, we will be working with ATD and Ministry of Digital Economy to do agricultural surveys. For financial data, we're really only able to use what we can get our hands on, so if it's publicly available, that's excellent. So in pretty much all of these data sets, there's going to be some challenges and some inconsistencies, and we're not really able to account for all of those. As I said, even with measuring road length, even in the US where we have excellent data across many different things, we still are lacking pretty basic data on where our roads are. And so you can imagine how something like your income, things of that nature are even more challenging. And I'm not sure if I answered the question other than to say it's a really challenging problem. And these are the types of biases that could exist in these machine learning models. And so we do need to study these problems, and we do need to understand how does the output from them affect people. But yeah, I don't know much more about African financial data, especially.
Je crois que la réponse tout à l'heure du commandant rejoint un tout petit peu. La précision n'est pas exacte, mais ça se rapproche un peu plus avec les données qu'on arrive à collecter. On a une deuxième question, mais je propose qu'on continue pour rester dans les temps. Donc, en ligne, on va essayer de répondre dans le chat directement pour les questions qui restent. Donc, on continue dans la salle pour l'exercice de groupe tout à l'heure. Et je voudrais préciser que sur le code QR, dans le formulaire, vous êtes invité à uniquement renseigner que l'adresse Gmail pour qu'on puisse vous partager le fichier Drive. Donc, uniquement l'adresse Gmail dans le formulaire sous le code QR pour pouvoir avoir accès au Drive. Merci.
Okay. Thanks. So now I'd like to switch to a demonstration. So if we can get the shared screen, or we can leave this up for a moment if people would like to scan this still.
Peut-on avoir, s'il vous plaît, l'écran partagé pour la démo qui était... S'il vous plaît, là. OK, merci.
Okay. So I am going to be going through a notebook. If the internet will allow me, I'm going to do it live. If not, the outputs are already there, so we'll be able to still see what would be happening, even if it's not exactly real time. But before we get started on how do we use mosaics, I'm going to go all the way back to the imagery itself. Did it stop sharing?
L'écran s'est arrêté ici. S'il vous plaît, pouvez-vous partager pouvez-vous partager l'écran du fichier Google Colab?
I might have been disconnected from the Zoom. So, yeah, I believe my internet cut out for a moment. Okay. Okay, I'm back on the Zoom. So if we could share, I'm sharing my screen. If you could switch to that. Yeah, might have cut out again. Sorry. I think it just keeps cutting out.
Peut-être en attendant, on remet le code QR ici pour ceux qui n'ont pas encore scanné pour remplir le formulaire. Pouvez-vous remettre, s'il vous plaît, le code QR sur les écrans en attendant? Merci. Donc, assurez-vous d'avoir rempli le code, le formulaire derrière le code et surtout d'avoir mis votre adresse Google pour qu'on puisse vous partager le drive. Yeah, I'm just going to do it from over here. It's okay. Ok, alright. Pendant qu'on règle peut-être le petit souci technique, j'aimerais peut-être savoir, est-ce que dans la salle, il y a d'autres questions qu'on peut collecter pendant ce temps? On va collecter ces questions, les noter, et après, on va trouver les réponses à partager avec vous. Donc, je vois déjà qu'il y a une main. Est-ce qu'il y a d'autres personnes qui aimeraient poser des questions par rapport à l'atelier mosaïque avant qu'on ne passe à la pratique? Ok, donc on va prendre les questions et je vais noter. Donc, essayez d'être le plus concis possible pour faciliter la prise de notes.
Ok,
merci.
Là, je vais aller en français.
Ok.
Dans la méthode d'entraînement de son modèle, il a parlé de patch, qu'il divise les images en patch. Est-ce que je voudrais juste savoir, les patchs auxquels il divise les images, est-ce qu'il considère tous les patchs de l'image? Et si oui, est-ce que cela ne fait pas trop de données à traiter pour les machines?
Ok, bien noté.
I don't need it, no.
Ok, nous allons voir s'il y a autre question. Est-ce qu'il y a une autre question à prendre pour répondre par rapport à l'atelier? Ok, je crois qu'il n'y a pas d'autres questions. Maintenant, je vais voir, est-ce que tout le monde a pu remplir le lien Drive? Est-ce que tout le monde a... Ceux qui ont pu remplir, est-ce que vous pouvez juste vous prononcer, s'il vous plaît? Ceux qui ont pu remplir le Drive. Ok, je vois qu'il y a quelques-uns. Vous avez tous accès quand même? Le code QR a fonctionné? Non? Ok, je vais prier encore la partie technique de garder le code QR à l'écran. Pouvez-vous garder, s'il vous plaît, le code QR à l'écran? Ok, non. Donc, essayez peut-être de partager le lien pour ceux qui l'ont. Essayez de partager ça aux autres qui sont à côté de vous, qui n'ont pas accès au Drive. Vous pouvez partager le lien à la personne qui est à côté de vous, etc., pour avoir accès au lien. Et une petite information aussi, c'est que sur les tables, vous avez, si je peux le prendre, vous avez ça, qui a le code QR dessus, c'est pour évaluer chaque session. Et donc, pendant ce temps, je peux vous inviter aussi à le scanner. Donc, à la fin de chaque session, vous pouvez scanner ce code pour donner votre feedback pour la session qui s'est déjà déroulée. Donc, ça, c'est une information à vous faire passer. N'oubliez pas de le faire avant de partir, à la fin de chaque session.
All right, sorry for the technical difficulties. Luckily, this did load before I ran out of internet. So I did want to mention that the satellite imagery also is very important in these models. And currently, the Mosaics API only has a single layer of features available. And the imagery that went into the API is currently displayed on the screen. And we can see that West Africa has trouble with cloud cover in this particular area. So we don't have as high quality features in the API. And that API was used to do the 120 maps that we looked at earlier. And most of the malaria data comes from West Africa. And so you could see why the malaria task did not do very well. And it's simply because the imagery was not as good. And so this is very important. Just as the label data going into the model is important, the input imagery is also very important. So here is the Mosaics API. We'll see if I have internet. But this is what it looks like. You can make an account, register, and then log in. I was going to go through actually uploading a file of coordinates to download imagery from the API. I don't think that'll be possible, but it is actually fairly straightforward. So sorry about that. So now I want to get on to the demonstration of using this technology. And so we're going to look at the artisanal and small-scale mining, which was the maps we were looking at earlier. But I'm just going to zoom in on Sierra Leone, because we have a lot of training labels from that country. And so our model predicts pretty well. So I want to start off with just talking about Google Collaboratory. So this is a cloud-based, interactive Jupyter Hub environment where you're able to run Python code or R code. You can upload your data, you can connect it to Drive, and it provides free compute power. It even provides a small amount of graphical processing unit if you're going to do more complex models. So it's a very handy tool for doing this type of work. So this notebook is connected to my Google Drive, so my data is stored there. So essentially what I'm going to do is just run some code. It's not connected to the internet right now, so it's not actually working. But you would set up your Python environment with the libraries that you would want. You would connect it to your drive and define like the file paths that you would like to access the data from. And then in this case, we're going to load in our artisanal scale mining labels. And so this data set here has latitude and longitude, as well as what country it's from, and then the sample type, which is just how we created that sample. And in this case, we actually did create the labels. We paid research assistants to look at very high-resolution satellite imagery, and in an interactive app, they drew polygons around suspected mining activity. And so we're able to get a label of whether or not there was mining activity, as well as how confident they were in that label. So you can see that there's some that it's on a scale of 1 to 5. There's some places the imagery is maybe not high enough quality, or the activity is kind of ambiguous, so they give it a lower score. And then a label of either 1 for mining or 0 if there was no mining. So the first thing we do is we just filter out a few areas, like we're only interested in artisanal scale mines. And we have a bunch of data on commercial mines because that's like publicly available. You can just download that yourself. But we're not actually interested in commercial mines because we already know the footprint of those. But we want to look at small scale mines because we know that there is very limited data in this space, and oftentimes it's very low quality. And we also know that large shares of the global mineral supply are unaccounted for by only commercial mining. And so it's a very important economic activity that's very poorly understood. So we look at artisanal scale mines, which are often informal, unregulated, or unpermitted. And so after we filter it out, we just get a look at our labels. And we can see that the labels are very imbalanced for this data set, where we have far more negatives than we do positives. And so we have to be very careful about how we use this data and what sort of conclusions we draw from it. So the first thing we do is we take the geographic information. We have a latitude and longitude for every location, and we turn it into a small polygon. So first we turn it into a point, and then we expand it out and turn it into a polygon. And the point represents what we think is the center of the mine. So as we expand out, we are just encompassing the mine. And this is what our labels look like in Sierra Leone. It's still letting me do that. That's nice. So we can see that this data is also very clustered. So not only is it imbalanced, but it's spatially very clustered. All these green points represent artisanal scale mines, and all of the gray points are all negatives, where there just are no mines. This big cluster here is around, I might not get the name right, but it's, I think, Koidu town. It's a large commercial diamond mine. And we find that there are many, many small artisanal scale mines around that larger commercial mine. We also see down in some like river valleys and different areas that there's just more mining happening. So because of the distribution of the data and because of the imbalance, it is difficult to model reliably. So here we load in our satellite features, and this is what they look like. So you have every row is a physical location on Earth, in this case Sierra Leone, and we have feature 0 all the way to feature 3999. So there's 4,000 features, and each one of those carries a wealth of satellite information about that physical location. So in this case, I only printed the first 5 rows. but Sierra Leone contains about, I think it's about 60,000 square kilometers or so. So there's actually about 50 to 60,000 feature rows here. Next, we similarly make this into geographic data, where we have the latitude and longitude, and we make that into a polygon, and then we're able to use the geographic information to combine these features to our labels. But to pause for a moment, this is an example of a feature map. So this is just what does feature, in this case 0, look like when you plot it spatially. I don't have the best sense of what Sierra Leone looks like, but I could imagine these coastal areas might be towns or cities, so they might be picking up on things like buildings and roads. But like I said, I'm not actually very confident on what they represent, and it's because these features are randomly generated. We don't know what the input patch looked like, so we don't know what that summary is representing. If I was connected to the internet, I was going to plot several different ones, and you can see how they all look very different depending on which feature you look at. So next we actually join it, and in Python this is a very simple operation. We use the package geopandas to perform a spatial join where we have our labels connected to our features, and we're only keeping observations where they intersect. In this case we have, I think, about 4,000 or 5,000 labels, so we have about 4,000 or 5,000 rows of data. Next, we just do the actual machine learning portion. And in this case, to keep it simple, we are going to use a ridge classifier. So it uses ridge regression, which applies a penalty to the coefficients to minimize overfitting, essentially. So first thing we do is we split up our data. We define our x's, which are our features, and our y's, which are the labels. We split it up into a train and test set. And then we define our model. In ridge regression, there is only one hyperparameter, which means that there's one parameter that humans need to change. And we use a grid search method to iterate over those different parameters during cross-validation to optimize that value to get the best penalization of the coefficients. And I wanted to pause here because this portion could be replaced by any model that you're familiar with. One of the nice parts about the satellite features is that the way that they're generated means that there are already a lot of non-linearities built into the features themselves, which means that we can use a simple linear model, which tends to be very explainable. You can usually explain what the parameters mean, but you could replace this with a random forest, gradient boosting models, support vector machines, anything that you wanted. It's just there's typically not always a reason to do more complex models when the simpler one often will work. It is a binary classification problem, so another great option here would be logistic regression, which is maybe even more suited, but there's other reasons that we were using ridge regression, so I stuck with that. This model used 5-fold cross-validation for 4 candidate hyperparameter values. So we are fitting 20 different models, which is very simple, very small amount. This took about 1.5 minutes to 2 minutes on this free Google Collaboratory computing environment. On my laptop, it took 15 seconds or so. So it's very quick. Here's where we're going to evaluate its performance. We see that the best alpha parameter is actually just 1, which is a very low level of regularization, or a very low penalty, which means that this model is able to get at the weights very accurately without having to penalize them very much. In this case, Ridge classifier does not produce a predicted probability. So instead of just using the outputs from this model, we calibrate it with an isotonic regression, which is very quick. It takes milliseconds rather than seconds or minutes. And you can see in the plot our calibrated versus uncalibrated. It doesn't necessarily change the strength of your prediction, but it does turn it into an estimate of the predicted probability, and it also smooths out the receiver operator characteristic curve. So you can see that in this model, even just the uncalibrated model, we are able to explain about 90% of the variation in our artisanal scale mining labels with this set of satellite features. In this research, we did thousands of models. Actually, I think we're past 10,000 models. And so we're able to look at these AUC scores across a range of different ways of splitting the data, where we're stratifying it by the country that we're looking at, because there's more countries that we have available data for, or how our sample was collected, as well as how many labels are in each class. So you can start to get a picture of the uncertainty and account for the unbalanced nature of the data, as well as the spatial clustering. We can do like spatial cross-validation. This demonstration is a much simplified version of this. But this value, this 0.9 value, is right around the median value across many of our different simulations. So the next thing that we do is that we have imagery features for the rest of the country. So we can then apply the model to the full set of, I think, 50 or 60,000 feature values and make a prediction for every location within Sierra Leone. And using that isotonic regression, we're able to get a predicted probability. And so we can look at what that looks like. And so here are the predicted probabilities. These range anywhere from 0 to 1. And we don't apply any thresholding to this particular map, so you can get a sense of the full range. In our paper that we're using in the study, we actually use our labels to understand the percentage of area that has mining across our full distribution. And then we use that information to set a threshold value on our predictions, where we're able to mask out areas where we think that there is no mining. And that keeps it more consistent with what we already know from labeling the satellite imagery. You can also see that certain areas, I think this area, if you can see my cursor, I believe that is Freetown, which is more of a city. So you would not necessarily expect small-scale mining in the middle of a city. So you also have to take these predictions, you have to evaluate where these predictions are being made and make sure that it's accurate and makes sense. So there is a certain amount of intuition that you need to have about the area in which you're performing this analysis. So here's just some conclusions, as well as some further work and some acknowledgements. But I can pause here and just take any questions, if anyone has questions about this process or the modeling that we have seen.
All right. Merci beaucoup, Dr. Colon. Je vous prie d'ovationner, s'il vous plaît, pour sa brillante présentation. Et peut-être maintenant, 2 réactions dans la salle, s'il y en a un, peut-être du côté de la TD qui veut rajouter quelque chose. OK. Donc, on avait une question. On répond plutôt à cette question-là. D'accord. On le réinvite pour venir devant. D'accord. Donc, la question, donc, I think, Colin, you will need the helmet of... Donc, maintenant, j'espère que c'est bon, vous arrivez à écouter. Donc, la question concernait les patchs. Et donc, c'était de savoir, est-ce que, dans votre présentation, comme mentionné, est-ce que tous les patchs sont utilisés? Si oui, est-ce que cela ne fait pas trop pour la machine, peut-être sur apprentissage? Dans un sens, je crois que c'est bien la question. Sinon, vous pouvez la répéter. Est-ce que c'était bien ça la question? OK, c'est ça. Donc, vous pouvez répondre maintenant.
I'm sorry, could you repeat the question? I'm not sure I got the translation exactly.
OK, peut-être vous pouvez poser la question directement en anglais. Comme ça, c'est plus simple.
Okay.
So, thank you for the nice presentation. My question was, in your presentation, you talked about some patches, like you subdivide images into patches, and you consider all the patches. So I'm wondering if all the patches are considered in training the model, and if yes, so doesn't it do too much more tasks for the model or for the machine or for the laptop?
So the question is about the patches in the neural network? Yeah, so the way that works is we start with our sample set of imagery, and we just take small pixel values, so maybe a 3x3 matrix, and then across all of the different color channels. And then we use that to convolve, those are the weights in the convolutional neural network model. And so we draw anywhere from as little as 200 patches to as many as 8,000 in previous research. And so another thing that you can do is vary the size of the patch, which you can then get at different textures, different combinations of colors, and different things within that image. So you're able to represent a lot of information. So the more patches that you get, the more information you're able to extract. One of the other advantages of modeling the downstream tasks with like ridge regression versus standard ordinary least squares regression is sometimes we only have maybe a couple hundred training data points, whereas we might have thousands of features. And ordinary least squares, like simple linear regression, would not work in that case. But because ridge regression has the penalization parameter, you can have way more features than you do training points. But we have done some recent research where we look into varying the patch sizes, varying the normalization of the imagery, as well as stratifying where we're taking those patches from. So we have patches drawn from all over the world, or for very local problems. Sometimes we'll do just very local imagery. And we try to see what sort of effect do all of these choices have on the downstream models. And we find that it's usually actually fairly stable, but there are certain things that you can do to increase like your spatial extrapolation. So there's different methods that you can use that will actually make it easier for you to train in one location, predict in another. But yeah, it is under active research, like what is the best set of parameters, what's the best number of patches to extract. All of these things are important questions, and I don't think we have like a single satisfying answer, but we do see that there is, while there is some variation, it is relatively stable. And so it is, it does tend to be pretty reliable across those choices. I hope that answered.
All right, merci beaucoup. Le commandant a une réaction. Est-ce qu'il y a un micro?
Ask some questions online.
Okay, thank you, Cullen, for the presentation. We didn't see under the hood, so we like to understand which convolutional model you use for the future computation, and what is the size of the input image, basically.
Yeah, so that is an excellent question, thank you. The input images that are on the API use the Planet Labs. It's a pre-cleaned data set where the imagery is, all the cloud covers removed. It's quarterly, so they take images from a full like 3 months, and they make one single map that is very clean and very high resolution, about 4.7 meter resolution. And these are large base maps, and we crop out very small image chips that tend to be about 1 kilometer in size. So our input image scale tends to be 1 kilometer. There's no reason why you couldn't do smaller or larger chips depending on your task. So that's the input imagery. As far as the model itself, we use PyTorch with graphical processing, and it is a very, very simple model. If you wanted to do this type of image featurization yourself, there is a package called TorchGeo, which is an extension of PyTorch for geospatial problems, and they really specialize in satellite imagery. So this has a built-in class that's just called RCF. And one of the cool things about that is it offers several parameters that we didn't discuss. So one of them is how you generate those patches. And because they're randomly sampled from imagery, they're essentially just random numbers. And so another way that you can do mosaics is by just actually generating random numbers to use as patches, which is slightly faster up front, but it's, you know, in the order of seconds, not really minutes. But this package, TorchGeo, in the class RCF, which stands for Random Convolutional Features, allows you to choose whether or not you want to make those patches from a Gaussian distribution or to sample them from the imagery. And it also provides methods for doing that sampling, and it's incredibly fast. It's very, very quick. If you were to look at a simple definition of a random convolutional neural net model that we've used in the past, it's really only 10 or so lines of code. They're incredibly simple models. You know, there's no like back propagation or any fancy, very technical stuff. It just does one convolutional layer, one linear activation. We use ReLU. And then we also take the inverse of the convolution and use a linear activation on that as well. So you get kind of this 2-for-1 deal where you only have to compute 2,000 features, but because you inverse them and then activate them, you actually get 4,000 out of it, which even improves the efficiency even more because you have to do fewer convolutions. And then we use an adaptive average pooling method to summarize those pixel values from the activation maps. I hope that wasn't too technical.
All right, merci. On va prendre une dernière question dans la salle. Ok, demain, on va juste les prendre pour le moment en ligne. Nous n'avons pas de questions. Ça sera pour la deuxième partie. 2 questions dans la salle et puis on passe à la prochaine session.
Okay. I just wanted to know if there is an estimate of the runtime for this notebook, and if we have an estimate of how much it can cost if we were to build a real-time application based on satellite images, and if, for example, the patches that are used depend on the bands of the images, or okay.
Yeah. So I'll start with the time. The largest time component of the whole mosaics process is the image processing. So if your task that you're interested in can use pre-computed features, that's the ideal situation for mosaics. In the future, we hope to pre-compute more layers to allow for more things to be modeled. But the runtime for that notebook, if I were to actually run through it, took maybe 5 minutes or so. And part of that is just transferring the data to Google Colab. So if you don't have to do that, you can cut out a minute. If you have more processors to do the machine learning part, like my laptop is much faster than Google Colab, it could be run in maybe a minute on my laptop. It took about 5 on Google Colab. And then the second part of your question, I think, was the color channels of the input imagery. And so right now the API is only visual spectrum imagery, so just the red, green, and blue bands. In the features that go into the demonstration that we just used, we're actually using a different set of imagery technically. It's from Norway's International Climate Forest Initiative, which provides the same Planet Lab imagery with the near-infrared band on top of it. And they pre-process their imagery to be useful for forest, like deforestation modeling and that sort of stuff. So it is slightly different values than what you would get from the Planet API. But the more spectral bands that you include does increase the complexity of the model, and it could potentially increase the things that you're able to model with those features. The near-infrared, we found, does help quite a lot with mining. In similar research, we've looked at crop yield, and we found near-infrared is also incredibly helpful for that. And that's pretty intuitive if you've ever used things like NDVI to look at crop yield. And it just depends on the image source. And you know, with Planet Labs, how much do you want to pay? Because they don't offer the near-infrared for free. Like NICFI, it is free. Anyone could go and download this very high-resolution data and process it themselves. So it's a pretty cool program.
Ok, merci. On va passer à la dernière question éclair. Peut-être Monsieur Dr Colin est là, la pose aussi pour approfondir la question avec toi, Justin. Merci. Dernière question.
Okay, hello Dr. Colin, hello everyone. Thank you. My name is Said. I'm a GIS analyst, and I realized that the R square in most of the data line to human are really low. So I'm curious, like, is it the same R square like we use in mathematics? Because I have a biological background, and most of the time we have a confidence interval of 1%, 0.5%. So I'm curious, for mosaic, do you still use those data that have R square that are very low?
Yeah, and so this is the big question for a lot of statisticians is, what is a good coefficient of determination? What is a acceptable performance? And I don't think that there's an easy answer, although 0.9 sure does look a lot better than 0.6. But if you have other information that you could put into your model, you can start to increase the performance. So in our mining project, we also have geographic information about the land cover type or the minerals that that have been mapped, that sort of information. And we're able to build something of like an ensemble model where we actually use a random forest for the geographic covariates, and then we use imagery to do a similar model, and then we combine the predictions and we get the best of both worlds, which can increase our performance even more. So it really depends on what you're comfortable with for saying this is a good model. And one of the most important things about mosaics is it's usually not the best method. You know, it's not the most precise, but it is so much cheaper and so much faster and so much easier that it is an excellent starting point. And so, like you saw with the 120 tasks, we have a huge range of R-squared values. But what you can learn from that is not what exactly is mosaics good for, but you could more generally learn what can satellite remote sensing be used for. And maybe you find that mosaics isn't that helpful for your particular task, but maybe that gives you a starting point to then look at other ways to solve the problem that you have.
All right, merci beaucoup au Dr Colin. Je vous prie encore une fois de le raccompagner, s'il vous plaît. Merci pour la session. Et donc ça, c'était un peu l'atelier sur mosaïque, où nous avons un peu vu la combinaison des images, de l'imagerie satellitaire avec le machine learning pour relever les défis mondiaux. Nous avons notamment fait une démo avec le fichier qui est accessible sur Google Colab, que vous pourriez, auquel vous pourriez avoir accès, soit après avoir scanné le code QR. Je sais qu'il y a un petit problème de réseau dans la salle, donc peut-être pendant la pause, on peut remettre le code pour que vous puissiez scanner, et après, vous mettez votre adresse Gmail pour pouvoir avoir accès au fichier Drive. Donc maintenant, je vais passer quelques petites informations clés avant qu'on ne passe à la pause déjeuner. Donc la première information, voilà, avant de partir à la pause, s'il vous plaît, assurez-vous d'avoir éteint les casques afin qu'ils ne se déchargent pas pour la prochaine session et de les remettre sur la table ou sur vos chaises. Ça, c'est très important. On aura la deuxième partie de l'atelier sur mosaïque tout à l'heure après la pause déjeuner. Et nous aimerions quand même que vous continuiez par suivre l'atelier en français avec le casque. La deuxième information qu'il faut que je passe, c'est qu'on a besoin de voir le responsable de l'école Essen. S'il est parmi nous, le responsable de l'école Essen peut s'orienter vers l'accueil qui est dans le hall. Ou s'il y a d'autres étudiants de Essen, veuillez vous orienter vers l'accueil pour une information importante. Donc ça, c'est important. Essen, l'école, le représentant est demandé à l'accueil. Nous avons retrouvé aussi, entre autres, une clé d'un participant. Donc si quelqu'un a perdu sa clé, c'est ici avec moi pour récupérer ça. Et les dispositions pour le déjeuner sont les suivantes. Les hôtels sont en train de distribuer des tickets et le seul moyen d'avoir accès au déjeuner, c'est d'avoir ce ticket-là. Donc, nous avons un nombre qui excède ce qui est prévu, donc 250. Je tiens à préciser que, malheureusement, c'est seulement avec le ticket que vous aurez accès au déjeuner et je vous prierai de pouvoir comprendre cette disposition. Et voilà, on va essayer de gérer de la meilleure façon qu'on puisse le faire aujourd'hui ici, mais c'est seulement le ticket qui vous donne accès au déjeuner. La dernière information est pour moi de vous dire que la pause déjeuner va durer 45 minutes. On va essayer de rattraper un peu le temps qu'on a perdu. 45 minutes, je sais que c'est rapide, mais on va essayer de tenir dans ce temps. La pause déjeuner se passe à côté de la piscine, comme hier, et donc nous sommes tous invités à rejoindre le déjeuner là-bas. Nous allons revenir très rapidement, donc 45 minutes, pour continuer la deuxième partie de l'atelier sur mosaïque que le Dr Colin était en train de nous présenter tout à l'heure. Donc, dès que vous avez votre ticket, je vais vous inviter de rejoindre la place du déjeuner qui est sous la paillote à côté de la piscine. Avec la complicité de la région, on va mettre une petite musique en fond sonore pour cette partie-là. Je crois que c'est bon. Les intervenants sont disponibles toute la journée si vous avez d'autres questions aussi. Merci et bon déjeuner.
Hello. Hello.